Hi, I'm Rich with Inside HPC. We're here at ISC 13 in Leipzig, Germany, and we're here at the RogueWave software booth. And I'm here with Chris and Vince. So Chris, let's start with you. I mean, RogueWave, what do you guys bring to the table to the HPC community?
So RogueWave is a provider of software tools and components to make things easier for high-performance computing developers and scientists all across the industry. The main thing that we're talking about today, and I think during this interview, is TotalView, which is our C, C++, Fortran debugging tool, which we've recently, and we're very excited about, have adapted to work with a Xeon Phi, which is, sorry.
Well, Xeon Phi is a big deal these days. The #1 system on the planet, the fastest machine, is using Xeon Phi. And I think, Vince, this is where you come in, because you've got some rather large systems at Tennessee, do you not?
Right. I was going to say, we actually have the Beacon system, which is currently #1 on the Green 500. And what we have been charged with by the National Science Foundation is to bring users from all different areas of science and help them port and optimize their codes for the Xeon Phi. And of course, anytime you port or optimize something, you tend to break it. In fact, if you don't break it, you probably aren't optimizing it enough. And so what we have turned to TotalView for is the ability to figure out where it's breaking and why, what we've pushed on too hard. And we've been able to find some very interesting phenomena in people's codes as a consequence of being able to drill down to the thread level through something like TotalView.
You know, some of these problems don't even show up until you get to real big scale, right? Is that how it works?
That's true. Some of them don't show up until you get to big scale. For instance, one of the codes that I actually presented here as a best poster, Gyro, has never been dealt with in the tens and hundreds of threads underneath the MPI. And so what I was able to determine when I started to crank up the thread count and it started to die on me, it didn't give me any real obvious explanation, and it turned out that there was enough memory overhead that when I tried to do 100 threads, it wouldn't actually fit on the card. And so had I not had something like TotalView to tell me, by the way, you're running out of memory, I would have never been able to discern that, and we would have just continued to wonder what had gone wrong.
Now, you know, with the GUI of that, does it make it kind of accessible for mortals to work with this stuff? Because, you know, when you got hundreds of threads or even millions or wherever we're headed, how does that help?
Very much important, because if you have the GUI, especially with TotalView, you can switch between threads just by clicking. You can actually look at what state all your threads are in at a given time and start to find interesting patterns in there that you wouldn't necessarily be able to see if you were looking at print statements. Mm-hmm. Print statements are wonderful for some things, but when it comes down to really drilling down into a code, there's just too much information, and you need something like TotalView to help you sift through that.
Yeah. So when a customer like this comes to you, Chris, I mean, do they push the limits? They say, you know, we'd really like 10x of this kind of capability. How does that work?
Constantly. I mean, I think that's what makes high-performance computing, is that no one's happy with any number of cores or any number of processes. They're always looking for the next level. One of the things we've been very proud about is we've been pushing the envelope in TotalView with scalability. We did some debugging, not on Beacon, but on the Sequoia system at 786,432 cores, and that's not enough. So we need to keep pushing the envelope even beyond that. So definitely, I think that's one of the things that characterizes HPC is always wanting to push for just a little more performance, a little bit more power, and but to be fair, that's always in service of science, right? I mean, you're doing this with Gyro, not just to put up a big number on a slide. Though that's awesome.
Yeah, there's nothing wrong with that. But it is also in the pursuit of science, and that is, Gyro is a tokamak plasma code, and we'd like to eventually have nuclear fusion, and this is one of the opportunities to model that, simulate it, and make sure that 2015 or 17, when they build this guy in France, it doesn't suck the world in.
Yeah. Well, absolutely. A collapse of the space-time continuum, like on Fringe or something. Okay, well, I guess, kind of to wrap up, I posted a story today. There was a guy saying, are we missing the real challenge of exascale, which is getting code to scale it? That's really hard, and we really got to rethink this. Is this the kind of thing that the folks at your lab are looking at? How do you get to the, 20x or 1,000x?
Yes.
So
No, we're always looking to scale code. I mean, that's, in order to be able to stay ahead of the energy curve, in order to be able to stay ahead of the processing power curve, you've got to be able to scale not just in the simple several cores fashion, but in something like an accelerator, whether it be a GPU or Intel Xeon Phi. You've got to be able to take advantage of that high number of threads, vectorization, and those are things that what is old is new again, but we have a new generation of programmers trying to figure that out. And tools like TotalView are very assistive in helping them determine what sorts of optimizations are going to bear the most fruit.